Alright, so today we're going to be talking about some theorems and some formulas. Something called the mean value theorem, something called the mean value theorem for integrals, and then the average value of a function formula. Alright, but this first thing that we're going to do is actually sort of a fun activity. So go ahead and draw real large on your paper an XY grid, and then I want you to draw any continuous function. Alright, so it can be, it can look like something kind of like that, with as many peaks and troughs. Needs to be differentiable, so it needs to be continuous. And then, very accurate. Then we're going to pick point A and point B. Try to get this oriented. James, we're recording, right?
Mm-hmm.
So we're going to pick some point A, and then pick some point B. And we are going to connect them. I'll give you a ruler here. We're going to connect A and B with a secant line. And I'll give you a ruler to accomplish that. Toothpicks. Toothpicks. Alright, now here's the thing. I'm going to do something totally amazing. Alright? In fact, not only me, you are going to be able to do that. I bet that somewhere between A and B, in fact, I will say 100% guaranteed, if you drew a differentiable function, we could find some location, some C value in between A and B, such that the tangent line at C is parallel to that secant line. In fact, you might even be able to find a couple of spots. Alright, let me say that again. I bet we could find some location around here where when I draw that tangent line, and we'll represent the tangent line here with a little toothpick, okay, that tangent line is parallel to that secant line. So for me, I think there's going to be one actually right there. These are all negative, but then we kind of come up this way. I think there's going to be another one right about there. And then right, kind of almost leads off the top right about there. There'd be one there that's parallel with that. There'd be one kind of as it comes to the top here. Not on the negative side, but on the positive side. Yeah, mine's going to have 1, 2, 3, 4, 5, 6 locations where there is a tangent line that is parallel to the secant line. If there is, feel free to use toothpick to. Well, right, but that's not in between A and B.
Oh, between A and B,
So just put it there. Yep. So 1. Okay. Agreed. Now you try to beat me. Try to draw a new function where you think that is not going to happen. Yep, I see you got it here.
I think it's not going to happen?
Well, yeah, try to draw a function where it won't happen. See, because a lot of y'all had it where it's kind of almost. Yeah. All right. So does everybody have at least one toothpick on the paper?
Mm-hmm.
Yeah. let's try to draw one that's gonna beat the toothpick. All right. So maybe something not too crazy, just something looks like that. There's B. There's the secant line. I think I'm going to have one parallel.
Yeah.
Negative, 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 0, positive, positive, positive. Oh man. That's about right there, right? So that's a C value. What's another one? What if we just drew a straight line? Oh. Well, I got news for you. If it's a straight line, then this point right here has a tangent line that's parallel. This point right here has a this one right here has a tangent line that's parallel. This one right here. See what I'm saying? Every point on a straight line has the slope equal between the slope between the two of the points. Yeah. James, you think you could beat the game?
No.
Now, the trick is that the function has to be differentiable. Okay? We could break it if we drew a function maybe that had an asymptote, or maybe a function that had a sharp turn, right? Because I could have this point right here and this point right here. Golly, this is really not a good line at all. I'm gonna have to redo this here in a second. Anyway, because you'd be like, all right, I need something where it's gonna be 0, and there's no, this is all positives and these are all negatives, so it's not 0. So, all right. Maybe I just wasn't careful enough. Okay, now we're good. I was gonna say this is a test, but then okay, yeah, so part of the trick is that the function has to be differentiable, all right? And if it's differentiable, then it's also continuous. And then the catch is that C has to be between A and B, okay? All right, so that was sort of like your fun activity sheet. Now we're going to actually write the notes down. So this is known as the mean value theorem, sometimes abbreviated MVT. And we'll draw a real nice picture here. Some sort of function, y equals f of x, some value a, b, and the secant line between them. So given that f of x is continuous, and given that f of x is differentiable, which actually that's a little bit redundant. If I could have just said if it's differentiable, because if it's differentiable, then we know that it's continuous. But anyway. And this right here is the secant line. So let's walk back to geometry. In geometry, when you had parallel lines, what did you know was the same about those parallel lines?
The slope.
The slope, the value of the slope. So let's think about the slope of that secant line. I'll call that m secant for the slope of the secant line equals rise over run. So y2 minus y1 over x2 minus x1. So that's going to be f of b, which would be this value right here, minus f of a all over b minus a. So given all that stuff, here's what the mean value theorem says. There must exist at least one C value where C is between A and B. Such that now how can we put this into words? The tangent line at C is parallel to the secant line connecting A and B. Well, that is word, so I'll put that down. Such that the tangent line at C is parallel to the secant line connecting A and B. The tangent line at C is parallel to the secant line. Now, what Ivan said is that means that the slopes are equal, right? So we have the slope of the secant line. So that's f of b minus f of a over b minus a. That's the calculus or mathematical notation for the slope of the secant line. What is the calculus or the mathematical notation for the slope of the tangent line of a function at C?
The derivative.
The derivative. So f prime evaluated at C. So the slope of the tangent line is equal to the slope of the secant line. There's one more way thing that we could say about this. This change in y values over change in x values, if you're looking at something that's a function of time, then what this represents right here is it's like you're changing y over change in time. Okay? So what that is, that's the average rate of change between A and B. So whatever it ended at minus whatever it started at divided by the time difference between the two. If it ended at 10, started at 2, that's a change of $8 maybe over the course of 2 hours, so $4 per hour would be the average. And then the derivative, as I mentioned way back when we were kind of dealing with derivatives, is the instantaneous rate of change. How much is it changing just at that moment? Instantaneous rate of change. So the mean value theorem says there must exist a time between A and B, where your instantaneous rate of change is equal to your average rate of change. And here in a few minutes, there's two other theorems we'll look at, and then we'll look at some problems. All right, any questions? All right, that's the MVT, mean value theorem. There is a similar theorem called the mean value theorem for integrals, and that's what we're going to look at right now. So, if you want to write a title here, mean value theorem for integrals. And I'm going to try to draw this again. I did it so beautifully on my paper, but I'm going to try to reproduce it here. 3 XY graphs with the same function. Okay? So, I probably should just clone it, but hold on. And I'm going to kind of make this, it's going to be kind of cubic, kind of sinusoidal. So there we go, something kind of, sort of a little bit of peak and a trough. Peak and a trough and kind of going up like that. And pick A. They're kind of towards the peak, I guess, and then B a little bit higher. A. B. Some point over there. All right, so the mean value theorem that we talked about a minute ago dealt with slopes. The mean value theorem for integrals deals with area. And we'll assume that in each one of these cases, this obviously is the function f of x. Over here, I'll go ahead and write down the given information. So we've got this sort of obvious thing. F of x is continuous. F of x is differentiable. And based on our calculus knowledge, the exact area under f of x above the x-axis between a and b can be written as, go ahead, Ivan.
The integral between a and b of f of x dx.
Right. Okay. So just imagine what that actual area would look like. What I'm going to do is I'm going to do a sort of two approximations here. So this first approximation of the area under the curve, I'm going to pick A as my endpoint. And I'm going to draw a rectangle there that is as high as A is. Now, how do you think the area of that blue rectangle matches with the actual true area under that curve? You think it's an underestimate, an overestimate, or about right? Here, I'm trying to make it an underestimate. Does it kind of look like an underestimate? Because we have all sorts of this region right here that we're missing out on. So I'll put area of the rectangle is less than the true area. Now I'm going to choose B as my endpoint here, and I'm going to go straight up here and come across here. What do you think about the blue rectangle now as an approximation for the area under the curve?
Overestimate.
Overestimate. So here, area of my rectangle is greater than. Now, how did I choose the height in this one over here? How did I choose the height?
F of A.
F of A, right? How did I choose the height over here?
F of B.
F of B. Now, since my function is continuous and differentiable, if this one with choosing F of A is a underestimate, and this point up here for approximating the area is F of B, and that's an overestimate, doesn't it kind of make sense that there must be some point in between A and B, we'll call it C, such that if I go up to that point on the function, that would be an exact match for the area under the curve. So in other words, I pick my height to be over here on A, and it's an underestimate. I pick my endpoint over on B, and it's an overestimate. Well, then surely there must be some point in between A and B that I can pick to go up to my height, and I'll get exactly the right number. Just think about that for a second. Roger, what do you think? Does that sound kind of...
Yeah. So you're saying like anything anything in between A and B at any point, what you're saying? Or you're
I'm not saying at any point. I'm saying there must be at least one spot, just like in the previous activity we did. I said there's got to be at least one place you can put that toothpick where it's going to be parallel. There might be multiples, but surely there's one spot where the slope would be a match.
Right.
What I'm saying here is there's got to be at least one of these values. Now if I choose this one right here, if I choose this C right here, and I go across and I go that high, then I'm in an underestimate. Okay? In fact, if I choose this one right here, I'm an underestimate. Here I'm an underestimate. Here I'm an underestimate. Here I'm an underestimate. If I choose this value up here, I'm an overestimate. If I go here, I'm an overestimate. If I go here, that high, I'm an overestimate. Overestimate, overestimate. Well, as those two things are kind of getting closer and closer together, underestimate, 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 overestimate, overestimate, overestimate. At some point, they're going to kind of converge, and
right.
it's going to be an actual correct estimate. Does that make sense?
Yeah.
And that's what the mean value theorem for integrals says. It says, given all of this stuff, make sure I write it down exactly right here. There must exist at least one C value where C is between A and B, such that the area of the rectangle equals the area under f of x. The area under f of x, we already saw that was this expression over here, integral from a to b of f of x dx. What do you need, Rodney?
No, I just didn't know if that was new or on the right side. You just write that. Oh.
I just started writing that, yeah. This says there must exist at least one c value where c is between a and b such that the area of the rectangle equals the area under f of x. What's the formula for the area of a rectangle?
Base times height.
Length times width, base times height. You're all true. So the base, so to speak, is going to be the difference between b and a. So b minus a. The height is going to be f of c. So there's got to be some c value such that it's equal to, when you plug in c into the function, you get that height. You take that height and you take this width and multiply them together, and you're going to get the exact area under the curve. Alright, so the mean value theorem is pretty interesting. This value itself, this f of c, has some special meaning, and we'll see that here at the end of our next theorem. So these theorems by themselves aren't necessarily always, in isolation, not really good, but they're always, like all theorems are good when used in sort of a situation. But I've got to kind of show you how they kind of come up with this. Now, what we're doing right now is sort of like, I would call it sort of like an idea level, sort of conceptual, visual level. In the book, they are a lot more rigorous in terms of these, this has to happen and this has to happen and this is the reason why and things like that. But if y'all are okay with kind of getting the big idea here, if you want to go and be a math major and go ahead and prove some of this stuff, then you can dig into that. I don't know if that's in any of y'all's future at this point, so I'm more concerned you kind of get a move on. All right, y'all ready for the third one? All right. This one, I think, is a good one to end on because it's the most helpful of everything. All right. So anybody drive a car? Either your car, parents' car, other people's car. All right. So y'all are all seniors, so we can't use how old you are because probably the average age. If we're trying to find average, then you're all like 17 or 18. So okay. All right. Well, anyway, it's end of semester. We're all thinking about grades, right? And we're all thinking about averages. How do you find the average of a set of numbers?
You divide.
You add them all up.
Yeah.
Add them all up and then divide by the number of numbers, right? Okay. That's great when you have a specific set of numbers. Like when you've got like 5 numbers or like even 200 numbers. You can use a program. You can use a computer. You can use somebody who's working for you. Add them all up, right? It's no big deal. But what if you've got something that is a continuous function? So here we go. So we are looking at the average value of a function. We'll draw a little friendly function here. What if I've got some sort of relationship here, y equals f of x, and I want to add up this number plus this number plus this number plus this number plus this, right? I want to add up all those values. You're like, okay, no big deal, just add up those values. But this is a continuous function. So that means there's actually a value in between this one and 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 in between this one. Okay? So you thought it was going to take you about 2 minutes to add them all up. It's really going to take you 4 minutes, okay? But wait, there's more. There's actually a point in between this one and this one and this one and this one and this one. You see where I'm going with this? How long is this going to take us? Add up all, this y value and this y value. How long is it going to take us to add all those up? It's going to take us a long time. It's going to take us forever. Because we're never going to be able to stop, because there's an infinite number of points between A and B, so there's an infinite number of y values, and we're going to need to add up an infinite number of things. See where this might be a problem? And then it gets even weirder. We're going to divide it by, I can't believe you missed that. But anyway, the number of numbers. And James, how many numbers are there in between A and B? So we're not only going to have the problem of adding up an infinite number of numbers, but we're then going to have to divide it by infinity. See where that might be kind of an issue? All right. So you might say, well, Mr. Yoder, there's then clearly no answer to this. There's no way we can find the average value. And I'll be like, come on now. It's going to be like somewhere around here. Right? I mean, you're starting off here, and you're ending up here. I mean, on average, probably right about there. Would y'all agree with me? I can do that in my head. Why can't we just get the math to match it? I mean, I know that this is kind of hangs out a little bit. These low ones down here kind of cancel out these ones, but these up here are so high that they kind of are a little bit more. So it's probably going to be a little bit higher than that one down there. Done, right? So surely we get some mathematical tools to kind of do that, and we can. So here we go. So the average, well, y'all just said it's the sum, the summation, add them all up. Now you remember your mathematical terms, sigma for summation. So add up all the numbers, and then you divide it by the number of numbers. There you go. How's that for your mean? All right, so let's go ahead and do some notation here. So we've got A, and then I've got x1, and then I'll have x2, and then I'll have x3, all the way through all those guys. And so x1 is going to have his y coordinate f of x1, and x2 is going to have his y coordinate f of x2, and x3 is going to have his y coordinate f of x3. Now, in between any of those two x guys, we're going to call that delta x, which is sort of like we've been doing all semester long. So the difference between those two. And then how many numbers do we have here? I've got 3 there, but we'll say the number of numbers equals n. I've got 3, but we might have, if I extend this out, I might have like 7 or 8 or something like that. In reality, that's good for like a 7 or 8 number approximation. We could go with a 10 or a 20 or something like that. So here's a good formula that we've seen before. That width, delta x, this region right here, is equal to the whole distance between B and A, so B minus A, divided by the number of regions that I want to have. So B minus A divided by n. Multiply both sides by n, divide both sides by delta x, and you get the equation n equals B minus A divided by delta x. So the number of numbers n is equal to B minus A divided by x. So here we go. So our average value, the average of all those y values, is going to be f of x of 1, so this one, plus f of x sub 2 plus f of x sub 3 plus f of x sub 4 plus f all the way up to f of x sub n divided by the number of numbers, which is n. James, that makes sense to you? Okay? So now we'll kind of get a little bit mathematical on here. So I'm going to write that summation, that sum, as a summation statement. So I'll say the summation from I equals 1 n of f of x sub I divided by, instead of writing n, I'm going to write b minus a divided by delta x. I don't like fractions of fractions, so I'm just going to write that numerator again. Summation I equals 1 to n f of x sub I times, and then flip this, reciprocal denominator, delta x divided by b minus a. All right, that's pretty good formula there. Okay, that's going to be the average. You know, if I say I want 10 points, then I would say, all right, you know, this one plus 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 that, right? Kind of see what's going on. If I wanted 100 points, then I would go from 1 to 100, and so I'd figure out this one plus this one plus this one plus this one plus this one. You know, add all those y values up, and then divide by 100, right? But what I'm interested in is not just for 10 points. What's the average of all those if I had 10 points? Not just what's the average if I had 100 points, but I want to see what's the trend going to. If I take 10 points, what number do I get? If I divide this up into 100 points and find the average, what value do I get? If I take this and divide it up into 1,000,000 points and find the average, what value do I get? Okay, and then of 10 million, and then of 100 million. Okay, divide it up into 100 million spots and then find the add all those numbers up. You see what I'm saying? All right, what process am I describing?
Limit.
The limit process. So what I really want to do is I want to apply the limit process to this. I want to say, what happens as that n, that number of samples, so to speak, approaches infinity? Not A, average. Average value of f of x equals the limit as n approaches infinity of that thing right there, of the summation from I equals 1 to n of f of x sub I times delta x divided by b minus a. Now, quick question. Is b minus a affected by this summation? No, because it's not. I mean, that delta x, or that x sub I, that just thing changes every time. So I can pull this b minus a outside of the summation. Is b minus a affected by the limit as n approaches infinity? Also no, because there's no n term there. So what I can do is I can actually pull this b minus a out front. So 1 over b minus a times the limit as n approaches infinity of the summation from I equals 1 to n f of x sub I times delta x. Now you may recognize this. We talked about it briefly when we were kind of passing by. This is the y value, so how high it is. This is a delta x, a very small base value, right? So think of it like this is your f of x sub I, and then this is your delta x, right? So, we're adding up the height times the base, right? That's the area, right? That's the area of one of those little rectangles. And we're saying, what's the limit of the sum of all of those? Well, we have a mathematical formula for that. For the limit of a sum. What's that notation? James? Not sure. Rigel? Adding up all of the area of the rectangles. So this rectangle, plus this rectangle, plus this rectangle, plus this rectangle. So this is adding up, this is a sum. The area of the rectangles, the height times the base. And then seeing what that approaches, what happens as your number of rectangles approaches infinity and those widths get really, really small. James, you give it a second shot? It's the integral. Yeah, okay. This is the limit notation of the integral, the limit of a sum. So, that's really interesting because we have the. Turns out that the integral is going to help us find the average value of a function. You say, Mr. Goddard, I can't add up an infinite number of things and then divide it by infinity. And I say, yeah, you can. Right there. That's the formula. Just like you might have said, Mr. Goddard, I can't find the slope of one point. You have to have 2 points to have the slope. Oh, yeah, you can. With the limit. Limit of the secant, slope of the secant line. So, let's look at one problem very quickly. This says, for each problem, find the average value of the function over the given interval. All right? So I'm looking at this function, x cubed minus 3x squared plus 4 on the region from 0 to 3. Now y'all just talk to me real quick. What is the lowest y value in between 0 and 3 that we see here? What's the lowest y value?
0.
0. What's the highest y value that we see? 4. So if you were to make a guess, what's the average y value between here and here? Maybe 2. Okay, if we spend just as much time above 2 as we do below 2, right? But here's how you can know for certain. Average value equals 1 over b minus a, 3 minus 0, times the integral from 0 to 3 of f of x. X cubed minus 3x squared plus 4 dx. It's literally just applying the formula. You've got a calculator, you've got that Desmos tools to be able to calculate the integral, okay? So I think you're good to be able to solve those set up and solve those problems.
When does this due for you?
Wednesday, I guess. So right now we're looking at, we're talking about 3 things: average value, mean value theorem for integrals, and the mean value theorem. Thanks for watching.